Hello everyone, welcome to the next installment for the Psychotic brake build series. At the end of the last video, I was discussing how I might not have enough battery capacity to run the weapon full speed for the full 3 minutes. So in this video, let's talk about battery capacity, how you calculate it, and how you determine if your battery is going to be big enough for your bot. In general, for this video, I'm going to be focusing mostly on spinners or bots that have a weapon. For bots that don't have a weapon, it's usually a lot easier to calculate, and I'll talk a little bit about that further along in the video, but most of what I'm talking about is going to be applicable for both, but it's going to be a little bit more focused towards spinners because that's traditionally what I build. Additionally, pretty much everything I'm going to be talking about in this video today is applicable for insect size classes like a 1 pound or a 3 pound, as well as heavier robots like a lightweight, a featherweight, or even a heavyweight. The rules all still apply. It's all pretty much the same thing. So before I get into explaining all of this, let's kind of continue with where I left off with Psychotic brake. Where I left off with Psychotic brake is I did some weapon testing with the wood platform and the wood chassis, and I found that at top speed I was drawing about 31 to 32 amps worth of current. Now if we do the very quick math, we find that 3 minutes divided into 60 minutes is 0.05, so that's 0.05 of an hour. Batteries are always rated at amp hours, so if we do 31 times 0.05, we get something about 30 times 0.05, we get 1.5. That means I need a 1.5 amp hour battery. Well, the traditional size battery that you're going to be using in a Beetle is typically about a 1 amp hour, and that's what I'm using here. So it's some percent less than what I need. I need something that is actually 50% larger than this. I need a 1.5 amp hour if I want to run that weapon for the full 3 minutes. Now, we'll get into that later. You don't necessarily need to spec it like that, but that is a little bit higher than I would like because I also have drive. I need to be able to drive around as well, so it's probably not going to work. So let's take a second look at Psychotic brake, because I did mention in the last video that the gear ratio wasn't exactly the final gear ratio. The current ratio that's in there is greater than a 1-to-1. I'm actually increasing the speed of the weapon blade from the RPM of the motor, and that's, I think, causing most of my issues. So let's change out the pulleys, do a reduction, which 1.25 to 1 reduction, which is what I originally planned, and let's see what the current draw does then. So as you can see, I've got the whole frame and everything in here. I have the same pulley up front, but in back here I have a different pulley. This is a much smaller pulley. This is one of the original ones that I wanted to use. I've kept the motor attached to the base, but kind of had to slide it back a little bit to increase the tension of the belt. And by moving the position of the motor, I can't use the top plate anymore, so I have a washer over here to keep this center stack from just kind of flying off the top, and then the motor back here is just kind of held in place by a little screw in the back, and it has, you know, an adequate amount of tension. But I'm going to have to run this with the top off just because things don't line up anymore. So let's see how that goes. I apologize for the screen not being easier to read on the power analyzer, but it's just really difficult going through the Lexan, so I'll read it out to you. So that's only 17 watts, or about 1 amp. 12, 17, 14. So let's just give it from 0 to full power and see where it spikes. I think 21 is the highest that I saw. So right at 18 amps is what I'm seeing. So that is drastically different than before, and that's really good. That's kind of what I was hoping. So 18 amps is the idle current at full power. Not bad. So you might be asking yourself, why the drastic change? That went from 31 or 32 amps at full speed down to around 18 and a half amps full speed. That's a big difference. And the gear ratio went from, let's just call it roughly 1-to-1 to 1.25 to 1. So this isn't anything drastic. It's not like a 2-to-1 or a 3-to-1 reduction. It's a relatively small reduction. Well, the thing that you have to keep in mind is that the RPM of the motor is somewhere around 9,900 RPM. It's like a 620, and I'm running at 16, and so yeah, it gives me 9,920 or something like that. So almost 10,000 RPM. So that's spinning at 10,000 RPM at a 1-to-1 ratio. At 10,000 RPM, you start to get considerable amount of wind resistance and air resistance as it goes up. And the issue that I was having previously with the PLA pulleys is that's just a lot of friction. The belt is moving very quickly across those pulleys. So you get a lot of stress and strain just based on the amount of friction at the pulleys and just the amount of wind resistance. Anything over, let's just roughly say 5,000 RPM, wind resistance is going to start to be a bit of an issue. That's why you always hear that death hum from spinning drums, is they're just cutting the air. And drums typically run at a very high RPM, so you just have a lot of noise, and just the amount of resistance from the air becomes a factor. So by slowing that weapon down, I think, we slowed it down 25%. I'm not going to do the calculations, but we're significantly slower now. So instead of being in this 10,000 RPM range, which was 386 miles an hour, the tip of the blade is moving at 386 miles an hour. It's a lot of air to cut through. By dropping that down, we significantly decrease the amount of friction at the pulleys and the amount of wind resistance. And the power of the weapon also decreases as well because we're storing less kinetic energy. But 386 miles an hour is really fast, way too fast. It's probably never going to get a good bite. It's just spinning too quickly. So I actually want it down closer to about 250 RPM or 250 miles an hour, and that's about where it is right now. Okay, so calculating actual battery capacity. How do you do it? So let's say I took my test. I'm at 18.5. That was my maximum current draw when I was at 100% speed. So let's say a scenario. In a match, I turn on the weapon within 1 second of starting, and I run the full 3 minutes just sitting at full speed. No one ever touches me. I never have to restart the weapon, and of course it works the entire 3 minutes. In this scenario, how accurate do you think this is? So what we need to do is we need to find out an accurate scenario of how the actual bot is going to operate during the match. With something like Psychotic break, I really seriously doubt that, one, it's going to be 3 minutes every single time. It's probably not going to have the weapon running at full speed for the full 3 minutes. I'm going to have to start it up and restart it, and it might die halfway through, things like that. So there's a lot of assumptions that we need to make. I'm also going to be moving, and the drive is going to be using that. So let's look at those scenarios, and we have to make a lot of assumptions about the robot, the driving style, and the fighting style, and then just kind of figure out how much power we're really going to use during the whole 3-minute match. All right, so let's talk about some scenarios that would happen in a match. I've got this bucket here. This bucket roughly represents the fight. It is used energy. It's just energy that's gone away. And this represents our battery, a nice, lovely little copperhead pint glass. So let's just assume for this demonstration that this is 1 amp hour. So the match starts. We have this much amount of power or energy in the battery, and we start up the weapon. Okay, so we do that, and then we're going to drive around a little bit. Oh, there's a pushing match, and then, I don't know, like the weapon stalls out. That uses a little bit, and then there's another little pushing match. We're just kind of just driving around trying to avoid them. Oh, and then they shove us, and then the weapon, spins up again, and then now we're just kind of idling at full speed. They're stuck. Maybe there's a count out, and I don't know, we're out. So during the match, you basically have a finite amount of power that is stored inside your battery. And as the match goes on, every single little thing you do is going to be drawing that power down. Spinning up the weapon uses some amount of power. Keeping the weapon spinning uses some amount of power. Driving along uses some amount of power. And each one of these things is a little bit different, and of course it's going to be impossible to determine how much driving you're doing. Like, we could make some calculation that is, oh, the arena size is this big by this big, and the bot can move this fast, and therefore it's going to move, a total of 1 mile during a thing, and how long does it take to travel 1 mile? We can do all that, or we can just have some really basic assumptions. So let's start by calculating how much capacity is needed for the drive alone. Now, the first part of this, I'm going to assume that you have a weapon attached. The weapon is kind of the larger part of this. Generally, when I calculate the amount of capacity I need for the drive, I just don't. I just calculate it for the weapon, and whatever's left over is for drive, and that generally works, as you'll kind of see for this calculation. But generally speaking, the amount of drive that you have is going to be highly variable. You're not going to be sitting there driving constantly the whole match. You're going to be standing still, waiting for the other guy. There might be a count out that you're waiting for, things like that. And, you know, not every match runs the full 3 minutes, so that is something else that you've got to factor in. So what I like to do is I like to look at the maximum current draw of the motor. And for Psychotic brake, I'm using a 20 amp ESC, and I've tested that I can get pretty darn close to that. So let's just assume 20 amps is our peak. Now, you're not always going to be hitting the peak. Motors draw based on the amount of load that they're experiencing. So if you just take the motor and hold it in your hand and drive it, you might only be at like 0.1 or 0.2 amps. You know, it's not going to be that high. Then as soon as you clamp down on that load, it's going to start increasing. The 20 amps is going to be either very hard acceleration, pushing against someone, maybe it's stalled or locked up, things like that. So what I generally like to do is do the maximum amount that you're going to draw, which is 20, multiply that by the length of the match, so it's 0.05 if it's going to be a 3-minute match, so 0.05. That gives us 1. So that's 1 amp hour, which is actually this battery. So generally speaking, if you had a drivetrain that was completely stalled out for 3 minutes, you're going to use the capacity of this battery, but that's not the case. So then what I like to do is multiply it by 0.2, which is 20%. Generally speaking, that means that in the match, you're only going to be using the capacity 20% of your total drive capacity. I don't know the better way to kind of explain this, but you're not always going to be driving, you're not always going to be under full load, and a lot of times when you're just kind of driving around, you're not using that much. You might only be using 10 or 20% of the overall power of that motor. So that's kind of my general calculation that I like to do, is 20% of the maximum for the 3 minutes. So 0.05 times your maximum times 0.2, and that gives us 0.2 or 200 milliamp hours, which is only 20% of this battery. If you're doing a lifter or something else like that that relies more on the drivetrain, you have much more into the drivetrain, I just use that same formula and change it to 0.5. So you're using 50% rather than that down rating of only 20%. And that's just kind of my general rule of thumb. So we've calculated the capacity that we're going to need for the drive, and obviously we're going to find that that's a lot smaller than what our battery is going to end up being. So the weapon is going to probably take the majority of the amount of capacity from the battery. So from my simple test earlier, we had 18.5 times 0.05, so that is 0.925, so let's just call it 0.9. So that is 90% of this battery if I just run that thing the whole the whole match straight. So if we kind of do the drive, which was 0.2, 0.9, 1.1, this is 1, that means that I can pretty much drive around and keep the weapon at max for the entirety of the match, like maybe 2 minutes and 50 seconds. That's pretty good. But what if you want to calculate this a little bit more accurately? Well, what I like to do is I like to look at the peak and then multiply it by just 0.8, just call it 80%. And the reason I do this is because spinning up the weapon uses a considerably more amount of power. Like that thing is peaking around 400 watts, which is almost double, 30, 35 amps when it's spinning up, because it takes a lot more energy to get that up to speed. But guess what? That weapon only takes about 2 seconds to get up to speed. So maybe only 1.5 to 2 seconds, it's actually pulling that much current, and then it drops off. So you're seeing, nothing here when the weapon is off, a big spike up to 30 amps, and then it kind of levels back down to 18, and then something hits it, you go back down to 0, and then you spin up again, it spikes, and it kind of comes back down. The match is 3 minutes. You might not go for the full 3 minutes. There might be a few times where you're not at 100%. You're down at like 80 or 70%. So my kind of general rule of thumb is 80% of the total. So 18.5 times 0.05 for the 3-minute match. That gives me 0.925, and then times 0.8. That gives me 0.74. That means in a 3-minute match, if I am spinning at 80% sometime, starting up maybe 3 or 4 times or 5 times, and hitting some people, stuff like that, it comes out to about 0.74. So if we do 0.74 plus 0.2, I didn't need a calculator for that. That is 0.94, right under the battery capacity. Now, you typically don't want to have it right at the battery capacity, but keep in mind we're talking about a full 3-minute match. If you have watched any of these events for any length of time, you know that most matches don't go the full 3 minutes. If I'm going full 3 minutes, I'm instinctively going to lower the weapon down to 70% or something like that to conserve power. I might not drive around as much, things like that. You just kind of got to know your scenario, know what your bot is capable of. If you're going to be doing a driving lifter control bot, you're probably going to be hitting 3 minutes a lot more, especially if you're against another one of you. So you might want to kind of figure that out and maybe have a little bit extra capacity. Maybe a 20% buffer of extra capacity is a good idea. However, if you're running in a beetle class, a driver pusher lifter, let's just say your max is 30 amp motor for your drive, 30 times 0.05 times 0.5, that only gives you 0.75. So by the previous calculation of 50% duty for the 3 minutes at a 30 amp motor current, you're still under the 1 amp limit. So yeah, that is kind of generally how I estimate the amount of capacity that I'm going to need for the weapon is 80% of the total, I guess the full speed current times the 3 minutes. So all this makes sense and is fine and dandy when you have all the stuff in front of you and you can test it. I know there's some commenters that are going to say that. Well, guess what? I thought about that and I'm going to put it in the video. So if you don't have this stuff in front of you, you can very easily estimate it. Once again, for the drive, you can look at what the stall current is. That might be indicative of what you're going to hit. The appropriately sized ESC is another good way to look. For the drive, I just pick the ESC that's going to properly drive the drive motor, and I just look at the max of the ESC. For instance, this case, it's a 20 amp ESC. I just do 20 amps and call it that. In reality, I just don't really even mess with it, but whatever. So 20 amp, you can just calculate it based on the ESC that you're going to be using, assuming that the ESC is properly sized for the motor. For the weapon side of it, almost every motor out there is going to have a peak. It's going to have some sort of rating on the website. So if you look at Hobby King, it has maximum wattage. It's even going to have recommended ESC, the capacity or the current for the ESC that you want to use with it, and it's also going to be the max amount of current that it can take. So you can use any of those numbers to give a rough calculation. Now, if you're looking at the max versus the idle, I'm calling it idle, you saw in there that I was pulling 18.5. It's a 16 volt battery. So yeah, 300 watts. That motor is capable of 500 watts. So what you could do is you could just downrate it. This is going to be very much up to your design. I am spinning a 12.5-inch bar. It's a big bar. And I know when I get the metal one in there, I'm definitely going to be hitting 500 watts. I'm going to be peaking out that motor on startup. So you got to know your design a little bit. A drum is going to have a lower MOI. It's not going to use as much power. So you could just look at the maximum current draw for that motor. So let's say that's a 500 watt motor. I could do 500 times 0.75, and that gives me about 375. So I could rate it based on that. So you got to make just some assumptions here. You're not going to be running the motor at full power for a spinner the whole time. And you're not going to be running it at full power when the weapon is up to speed unless you have a really serious issue with bad bearings or something like that. So you can maybe downrate it by 75 or downrate it by 25%, calling it 75%, or even downrate it 50%. Like in this case, if I had a much smaller weapon or if I had a drum, that motor would probably only be about 200, 250 watts when I'm actually spinning the weapon. This one just happens to be relatively long and large, so that's the difference. So if you don't have the motors in front of you, for the drive, look at the appropriately sized ESC that you're going to be using, or the stall current, either one of those. Use the calculations I talked about earlier, and if you're looking at it for a weapon motor, know your weapon, know what you're going to be driving. If you're running a really big weapon, maybe err on the higher side. If you're running a smaller weapon, err on the smaller side. Look at the max current and the max wattage of that motor and downgrade it down to 75% that or 50% of that to kind of get your idle current, and then do the same calculation that I showed you earlier, 80% times the full match length. And that should give you a rough calculation. Whew. So we covered a lot of things in this video. If you had one real takeaway, it's assumptions. The assumptions are going to be what gets you the final number that you need. You need to kind of assume your driving style. I am very aggressive when I drive. If you're a little bit more timid or whatever other word there is for that, a little bit more reserved. If you're more reserved in your driving style, if you don't have a really crazy weapon or you like to run it at 50%, there's all these assumptions that you need to think about. I'm not going to be able to calculate it for you because I need to really know the robot, really know the driving style and all those other things to put in the numbers and get the right answer out of it. However, general rules of thumb is that a 1 amp hour battery for a beetle is very appropriate, and somewhere around a 250 to maybe 600 milliamp hour is appropriate for an ant weight. Generally speaking, for an ant weight, you're just not going to be able to find a battery small enough for you. I know a lot of people running 350 milliamp hour, and they could easily go down to a 250. That's kind of the range that you want to be. If you're at a 1 amp hour for a ant weight, way too high, way too high. Go to a 500, something like that. Or why are you drawing so much current in an ant weight? So somewhere around 350 milliamp hour for an ant, somewhere around 1 amp hour for a beetle is a really good place to go. Once you start getting larger, it's so dependent on your bot. Crippling depression, just for the sake of discussion, uses a 3 amp hour battery, and I don't think I've ever depleted that in a match. It's more about the current delivery. That's another topic for a different day. So hopefully this gives you a good idea. The one thing that I want to mention that I just completely spaced is when I do the drive calculations, I'm assuming that this is for both motors, not just a single motor, for both motors. If you are using 4 motors, it gets a little bit more complicated. Maybe instead of calling it by 0.2, you can call it by 0.25 or 0.3, something like that. All of this is very general and just kind of getting you in the ballpark. The only way you're going to know any of this for sure is to go to a competition and have like 8 fights and record the battery after every single one. That's the only way you're going to know it is that variable. This is just going to give you a good ballpark to be in. So I think the next thing to do is keep tinkering with Psychotic Brake. I will do another video some point in time discussing batteries a little bit more in depth, connectors, charge cables, capacity I already kind of covered, but I want to cover discharge. That's another thing that we don't really talk about, and the number of cells, voltages, all that stuff. That is for a different video. Let's end this thing. Check me on Facebook, go down, click on links. I'll see you next time. Thanks for watching.